This is the first video in the completing the model of the atom unit. So far we have a very basic understanding of what an atom is. That has a nucleus, there's electrons around it, protons and neutrons make up the nucleus. But we want to have a more fuller and complete understanding of what the atom is. And the first thing we need to do in order to understand the atom and how we've arrived at some of the understandings we have today is to understand a few things about light. So you can see the first part of this unit, we are trying to understand light's dual nature. We'll understand we can look at light in a couple of different manners. There are three learning targets in this unit, and you can just read them here. The one we're going to focus on to start with is this first one. We want to be able to use the equations C equals lambda nu and E equals h nu to calculate an electromagnetic wave's wavelength, frequency, and energy. And actually, the only one we're going to be concerned about is this first one, the C equals lambda nu. We'll explain what that is. The E equals h nu we will get to later in the video, a later video, not in this video. And then we'll also hit the second learning target up in this video as well. So the first thing we need to understand before we actually get to any equations and how we use them is we need to just understand a few things about waves. Recall the short demonstration that you saw in class, or if you're watching this video before we've done the demonstration, we'll be doing one in class with a long spring. And we looked at some of the different ways that we can measure things about waves. And here's just a picture of a wave, and you can see a couple of things we might measure about it. One would be the wavelength. The wavelength you can see here is measured from the top of one crest to the top of another. We could also measure from the bottom of a trough to the bottom of the next trough. That would also be the same thing. And the definition for a wavelength is simply the distance between two equivalent points on a wave, and that could be measured in any unit of length. Meters, nanometers we'll be using a lot of, especially for visible light. That's a very common unit on wavelength. One thing I'd like to point out here is the symbol for the wavelength. This is the Greek letter lambda. It kind of looks like an upside down Y, so if you're looking for a way to write it, just writing an upside down Y would certainly be appropriate. Another thing that we can measure about a wave is its frequency, and that is simply the number of waves that pass a given point per second. A good analogy or a good way to think about frequency would be this. If you're on a boat in an ocean or a really large lake, and the boat is anchored, so the boat is in the same place in the water, it's not going anywhere, and if you just count the number of waves that pass your boat in a given time frame, whether it be in a second or a minute or an hour, you would be measuring the frequency. That is how I think the best way is to look at frequency. The symbol for frequency kind of just looks like the letter V. It's actually the Greek letter nu, spelled N-U. In this font, it just looks pretty much like a normal V. If you handwrite it, it looks a little more like a wavy V. I can show you in class if I haven't shown you yet. The units on a frequency are hertz, spelled H-E-R-T-Z. The symbol for that is capital H, lowercase z, and that is equal to a wave per second. So if a wave has a frequency of 1 hertz, that means one wave passes a given point every second. It might also be written simply as 1 over seconds, because if we're talking about a frequency, it's understood to be waves. Any wave, no matter what it is, whether it's a water wave or a sound wave or light, as we'll be dealing with a lot of light, there's a relationship that exists between wavelength and frequency, and that is this. The velocity of any wave, so how fast it's moving through space, is equal to its wavelength times its frequency. Now, for any electromagnetic wave, or light, that's what the fancy word for light, the velocity of that wave would simply be the speed of light. And the speed of light is noted by the lowercase letter c. You might be familiar with the equation E equals mc squared, one of Einstein's famous equations. That's the speed of light, and that is equal to 3.00 times 10 to the 8th meters per second, or 300 million meters per second. That is not something that you need to memorize. I will always give that to you on any sort of quiz or test, so you don't need to worry about memorizing it. What you do need to memorize so far that's on this slide are the symbols for the units, the symbols for the quantities. You want to know that the Greek letter lambda is this upside down y, that means wavelength. You want to know the V looking character, that's the Greek letter nu, is equal to frequency, and you want to know that c is the speed of light. And it's important to remember that. So if we just substitute in the symbols c, nu, and lambda into this equation for velocity equals wavelength times frequency, we get this equation. C equals lambda nu, where c is the speed of light, lambda is the wavelength of the wave, and nu, or the V looking symbol, that is its frequency. So we're just going to look at some examples here of how we use that equation, the C equals lambda nu. I would encourage you to work the problems right along with it, not just stare at the solutions on the screen. Maybe after each step, pause it, see if you can figure out what the next step is. So here's our first problem. We're told that microwaves are used to cook food and transmit information. What is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz? Now a microwave, as we'll learn here in just a second, is it's an electromagnetic wave. So that equation that we just looked at, C equals lambda nu, that applies here. So what we're asked to find here is the relationship between wavelength and frequency, which we just learned that was this equation here. The speed of light equals the wavelength times the frequency. So we want to solve that equation for wavelength. If I'm going to solve this equation for wavelength, I would simply divide both sides of the equation by the frequency, nu, and that gives us lambda, the wavelength, equals c divided by nu, or speed of light divided by frequency. Now I can simply substitute in my numbers. So looking back up at the problem, I can see that the frequency is 3.44 times 10 to the 9th hertz. And then c, that's a constant. Again, you don't need to memorize that. I'll always give that to you. That's 3.00 times 10 to the 8th meters per second divided by the frequency that's given to us. And now we can just solve it, plug it in your calculator, and you will get 0.0872 meters. Now you might be wondering how we get meters out of that. Well, it's important that we check our units. So if you look up here at the units, we have meters per second divided by hertz, which that's what we're showing down here, meters per second divided by hertz. But if you recall from the previous slide, 1 hertz can also be written as 1 over seconds. So what happens is the seconds cancel, and that leaves us simply with meters. Alright, here's another problem. We're told that light reflected from a green leaf has a wavelength of 490 nanometers. What is the frequency of the light? So again, it's a question of asking about the relationship between wavelength and frequency. So we're going to use this same equation, C equals lambda times nu. And then we just want to solve it for frequency this time because we're asked to find frequency. So I want to divide both sides by lambda. That's what gives us lambda equals nu equals c divided by lambda. Now I can substitute in the numbers. We have 3 times 10 to the 8th meters per second for the speed of light. And then notice here, we have to convert our units into meters. Okay, we can't leave it as 490 nanometers because that's not going to cancel with the meters and the meters per second. So we want to convert that to meters. So that's 4.90 times 10 to the negative 7th meters. Might want to go back and review some SI conversions. And we simply solve for the frequency, speed of light. We know it's 3 times 10 to the 8th divided by our wavelength, and we get our frequency of 6.12 times 10 to the 14th hertz. Checking our units here, we have meters per second divided by meters, so meters cancel. That does not leave you with seconds. Notice seconds is in the denominator, so you can't write your units as seconds because we're not finding a time, finding a frequency, and 1 over seconds, that is the unit hertz, so that works. Alright, one more lecture problem here. And we are asked to find the wavelength in nanometers of an X-ray with a frequency of 2.61 times 10 to the 18th hertz. Same thing, we're asked about the relationship between wavelength and frequency, so I want to use the same equation, C equals lambda times nu. And we want to solve that for wavelength, so I want to divide both sides by nu. We get lambda equals c over nu. Now we can substitute in our values, and that gives us 3 times 10 to the 8th meters per second divided by the frequency of 2.61 times 10 to the 18th hertz. And we can solve it, plug it in our calculator, and your calculator will tell you 1.15 times 10 to the negative 10th, and that would be in meters because seconds would cancel, but the question asks for the answer in nanometers, so converting that to nanometers, there would be a billion, or 10 to the 9th nanometers in a meter, so I just multiply it by 10 to the 9th. That gives us 0.115 nanometers for the X-ray. And then checking the units here, we have meters per second divided by hertz, which is the same thing as meters per second divided by 1 over seconds, so the seconds will cancel. That leaves us with meters, and then we convert to nanometers to get the answer that we're looking for. Alright, this is the end of the first learning target as far as what we're going to do today in this video, the C equals lambda nu equation. We'll be doing this second equation, the E equals h nu. We'll hit that one later in a later video. The only other learning target we'll hit up in this video is we want to be able to order waves in the electromagnetic spectrum by wavelength, frequency, and energy. So the electromagnetic spectrum, or electromagnetic radiation, which you commonly simply call light. The formal definition, the physics definition, you can read it there: an in-phase oscillation of electric and magnetic fields propagating through space. That's a mouthful, and it probably doesn't mean a whole lot to you, and that's fine. It's okay. We're not really going to use that as a working definition of what electromagnetic radiation is. Just think of it as energy. It's energy that goes through space. That is probably the easiest way to think about what light is. Here is a picture of what an electromagnetic wave would look like in a schematic. This whole idea of an in-phase oscillation of electric and magnetic fields. You can see here the red wave here, that's the electric field, and that is in phase with the magnetic field, that's the blue. The reason why it's in phase, you'll notice at a point where the electric field is at a maximum, the magnetic field is also at a maximum. And when the electric field is at a minimum, so is the magnetic field. That's why it's in phase. And you can see this is propagating together through space, the direction going to the right on this diagram. Now here's a short NASA video. I can't click on it here and show it to you. What I would do is I would just open up the PowerPoint yourself. You can get that on the website from SharePoint. Watch the video. It's only about 5 minutes long. Find some time to do that. Maybe not right now, but at some point over the next day or two, do click on that link and watch the video. I'll put a link to it as well on SharePoint, just directly, so you don't have to open the PowerPoint. I'll do that after I finish recording the video here. That way you can view it easily. It is a good video, I think. It's pretty simple, but it does a good job of explaining what the electromagnetic spectrum is. So the electromagnetic spectrum as a whole, it's a range of all the possible frequencies of electromagnetic radiation, or all the possible frequencies of light. When we talk about light in everyday life, and what you've probably almost always referred to it as, is light that you can see, or visible light. The thing is that's only a very tiny portion of the spectrum. I'll show you a picture here in a second that'll point that out. So just to give you an idea of how big the spectrum is, we're talking about wavelengths as small as 1 picometer up to 100 megameters. So a picometer, that is a trillionth of a meter, up to 100 megameters. That would be 100 million meters. So an incredibly wide range of wavelengths and frequencies. This symbol here, the capital letter E, just for your information, is the prefix exa. It's one that we don't use hardly at all in the SI system, but it means 10 to the 18th, so a huge frequency. Here's a picture of the electromagnetic spectrum, a schematic. What you can see here is just a simple categorization of the different frequencies and wavelengths. Starting here at the left of the spectrum here, you can see we have very long wavelengths, and these would be classified as radio waves. And then as we get a little bit shorter, we get to microwaves, and then infrared waves, or IR, commonly called IR. Then we get to the visible spectrum. This is what we can actually see. And then as we get even shorter wavelengths, we get ultraviolet, or UV. Then we get X-rays and gamma rays. What you need to remember here is you need to memorize this order from long wavelength radio waves to short wavelength gamma rays. And then down here at the bottom, it's showing us a scale in the frequencies. You don't need to memorize these numbers. You don't need to know that, for example, radio waves have frequencies of 10 to the 4th hertz. That's not important that you remember, or the wavelengths either. But what you do want to take note of here is the order of the visible light. Going from long wavelength to short wavelength, we can see the colors here. Red, orange, yellow, green, blue, indigo, violet. If you've ever heard the acronym or the name, the fictitious name Roy G. Biv, ROYGBIV, that will help you remember the order of the colors of the rainbow. That's what this is. Red, orange, yellow, so ROY, green, G, blue, indigo, violet, so BIV, Biv. Here. Looking at this, thinking about energy, just with some common sense, I think we would all agree that gamma rays and cosmic rays and X-rays, these have really high energy. Just think about this. If you get an X-ray, maybe you have a broken bone, maybe you go to the dentist, they make you wear a lead jacket or some sort of lead protective device over whatever's getting X-rayed, or around your organs so that you don't hurt yourself. Whereas radio waves and microwaves and radar, well, that's around us all the time. So higher energy is over here at this end of the spectrum. The shorter wavelengths would be higher energy. So going back to that question here, we want to order these waves by increasing energy, and you can take a look at those. So we want to start with the lowest energy and go to the highest. So maybe I want to pause the video, see if you can do that. Hopefully you got this order: radio waves, followed by infrared, and then green light, X-rays, and gamma rays. And then finally, we want to order the following waves by decreasing frequency. And so we're going to start with the highest frequency, work our way to the lowest. So highest frequency, that would be the longest wavelength. Highest frequency would be the shortest wavelength. I about got that backwards. So looking at our options here, we have orange, UV, microwaves, violet, and radar. I believe UV would be the shortest wavelength. Let's see if I remembered that right. Yes, UV is the shortest, followed by violet, then orange, then microwaves, and then radar. Alright, so we have completed the second learning target here, and that is the end of this video. We'll hit the next learning target, the third one here, on the next video for this slide.